Good morning, everybody. Today we are discussing the next topic of the stereochemistry, that is the optical isomerism in biphenyl. So, biphenyl is otherwise called as diphenyl. So, the biphenyl or diphenyl or phenyl benzene or 1,1-diphenyl or limonene is an organic compound and the general formula is C6H5 twice. See here, this is the structure of the diphenyl in which two phenyl rings are connected by a CC sigma bond. And we have already studied that the CC sigma bond, in CC sigma bond, the rotation is possible, and due to this rotation, we will get the different conformations. Since the phenyl group is a small group and the CC rotation is also possible in diphenyl also, and here we can see that there is no asymmetric carbon atom is present in this molecule. So actually it is an achiral molecule. See, in diphenyl, one of the phenyl ring are exist in a one plane and the other phenyl ring are exist in the other plane. So these two planes are mutually perpendicular to each other, but even then the ring will flip. That means the see here the whole capture, it is written that one of the plane I have shown by a whole capture in which that plane is exist in the plane of the paper. The next plane is mutually perpendicular to that plane. So if a ring flip, the paper plane will exist in a perpendicular direction, and the remaining plane which is in perpendicular in the figure is converted into the paper plane. So then only that is the flipping of the two ring of the phenyl ring in diphenyl. Then the biphenyl, we can convert the diphenyl into optical active. So what are the method for making the diphenyl as an optically active compound? For that we have to arrest the CC rotation or CC ring flipping, and the one of the method for arresting the ring flipping is substitute the ortho position of the phenyl ring by a bulky group. So if it is a simple atom, if the substituent in the ortho position is a simple atom like fluorine, you know that it is a very small molecule, very small atom. That's why the ring flipping is cannot be arrested by substituting the fluorine in the ortho position. So we have to substitute the ortho position of the phenyl group in both the phenyl ring of the diphenyl with a bulky group, and that can be used for arresting the CC sigma bond rotation. So there are some molecules that do not containing chiral carbon but they are optically active. So example is the ortho substituted diphenyl. So in some ortho substituted diphenyl are locked into one of the two chiral and enantiomeric staggered conformation. And this type of the isomerism in biphenyl is known as uptrop isomerism. So the uptrop isomerism means it is a chiral molecule, appear to be a chiral molecule, and it shows the optical isomerism due to the lack of chiral carbon atom. That's why this type of the isomerism is known as uptrop isomerism. Then in order to make the diphenyl as an optically active compound, there are the diphenyl must satisfy the two conditions. First one, the ortho position of the phenyl ring, both the ring or any one of the ring must satisfy must be a substituted group. And the second condition is that the diphenyl do not have a plane of symmetry. These are the two conditions for optically activity in diphenyl. So first we move into the first condition. See here in the diphenyl we can see that the both ring are substituted with a with a group. See here, in the first ring it is ortho position is substituted by A and B. In the second ring it is substituted by X and Y. If it undergo the ring flipping, if it is another pair of the enantiomer, it is exist in a different plane. So these are the stereoisomers possible for the diphenyl. So this is the first condition. For the optically active compound, the substituent in the ortho position must have a large group. If three bulky group present on the ortho position, then causes the restriction of the CC sigma bond rotation, and the group are large enough to interfere mechanically, that is to behave as an obstacle, then free rotation about the single bond is restricted. Thus the two benzene ring cannot be coplanar. So the third condition is both the ring of the diphenyl compound must be a non-coplanar. Okay. So in diphenyl we can see that one of the ring which is exists in the plane of the paper, the other ring which is shown in the dark color is in the out of the plane. So if we take the mirror images, we will get a non-superimposable mirror image. So that's why it is an optically active compound and it do not have a plane of symmetry. So how we will take the plane of symmetry here? I have shown the two plane here. One plane exists in the one ring of the phenyl ring is exist in one plane, and the other plane contain the remaining phenyl ring. So if we take the first plane, that is I have shown by a hole capture, and if we take that plane, the next this plane is mutually perpendicular to the next plane, so it will cut, the first plane will cut the remaining plane just by middle. So we will get a two half, and both the half are not identical in character, so it do not have a plane of symmetry. So in the substituted compound, okay, I have shown here, if we take one plane like as shown by the figure like this, and if the ortho position are substituted by the different group, we will not get any plane of symmetry here. That's why it is optically active. So one of the condition for the optical activity, the ortho position of the both the phenyl ring are substituted with a different group. If it is a same group in the ortho position, we will have a plane of symmetry. So it is not optically active. So first condition for optically activity in diphenyl is that both the ortho position of a single ring must be different. Okay, substitute which is attached in the ortho position of the phenyl ring must be different. First condition. Second condition, both the ring must not be a coplanar in character. The third one, there is no plane of symmetry. Okay. Then the other method for making the diphenyl as an optical activity is that instead of ortho position, we can also substitute in the meta position. And the condition is that the same condition, the meta position is substituted with a different group. Okay. Then the third condition, we can here in the first example, we can connect A and B by using a chelating ligand. So the CC sigma bond rotation is also arrested. These are the different methods for making a diphenyl as an optically active compound. And I am also discussing how we will observe an optically active molecule. So if you are observing the ring through A dash B dash ring, so we will get the Fisher projection formula like this. Okay, if you are observing the molecule in A dash B dash plane, the ring which contain A dash B dash substituent, so we will get we can see A in the upward direction and B in the downward direction, and A dash is in our right hand side and B dash in our left hand side. Okay, so we have to substitute like this. So we will get a Fisher projection formula, and in the Fisher projection formula we have to assign the priority to the first two group in the first two group in the first ring, and then the remaining the 1 and 2 in the remaining group. So we will get the optical activity in biphenyl. If the substituent are rotating in the clockwise direction, then we will get a R variety. If it is in the anti-clockwise direction, we will get a S variety. Thank you.